want to give you a little introduction into chapter 12. And the great thing about chapter 12 is it's very similar to stuff we did in chapters 10 and 11. So I want to start with what we did there with a hypothesis test. We said the test statistic equals the statistic minus the parameter over the standard deviation of the statistic, which is also called the standard error. With the confidence interval, we said it's the statistic plus or minus a critical value times the standard deviation of the statistic. So I want to walk you through what this is going to look like in chapter 12, what this is going to look like with a proportion problem. So in chapter 12, what is the statistic? What symbol do I use for a statistic with proportions? P hat. And the parameter is the true P. And how about this? The standard deviation of the statistic. Now you may think, I can't remember. It's like sigma over square root of n. And then you think, no, that's for means. So you check out the formula chart until something on there looks sort of familiar. And you recall that the standard deviation for proportion problems is that. Now, did I replace a sigma with an S? No. So I still use Z. I'm back to the pink chart. I'm back to the Z distribution or the normal distribution. Now let's walk through the same thing with the confidence interval. What's the statistic? P hat. The critical value is going to be Z star. And then the standard deviation of the statistic is that. Now, in all honesty, if we were doing this in college, I would spend about 1.5 days on chapter 12 and I'd give you a test. Or probably more to the point, I'd spend 2 days on chapter 12, 2 on chapter 13, 2 on chapter 14, and I'd give you one test that covered all of them. But we're in high school and we take things a little bit slower, a little bit more stepwise. I'll teach for a couple days, I'll give you a quiz, we'll take spring break, I'll review, I'll give you a test. That's kind of the way it'll look. So I want to work through a problem, or at least the basics of a problem of both of these types with you. Somebody give me a context for proportions. What's an example we could use to work a proportion problem out? The proportion of what's? Chickens to ostriches. Okay, so you go to a chicken farm and you get the wrong shipment in and it looks like you've got a bunch of eggs and you're not sure perhaps what they're going to grow into. So you thought that you were going to get maybe 40% ostriches. Your null hypothesis is you should end up with 40% ostriches. The alternative hypothesis could be perhaps not equal to 40%. So we'll work through this problem here. How many eggs am I looking at here? 45 eggs. And how many of them turned in to be ostriches? 27. Okay, so here's what happened. I thought that this company usually gave me 40% eggs. I got this huge giant shipment, but I checked out 45 of them, and 27 out of the 45 were ostriches. Do I have evidence that they're no longer sending me a 40-60 ratio? And so I'm going to set up the problem here. Z equals estimate minus parameter over standard deviation. And then from here, I'm going to grab my calculator and do a one prop Z test with this information. So I go stat test one prop Z test on this calculator. That's number 5. My P naught, the original P that goes with HO, is 0.4. X, which is the number of successes, is 27. N is 45. I'm doing a two-sided not equal to test. Calculate that dude out. I get my test statistic. And I get a p-value of 0.006. Small p-value tells me to reject HO. I now decide the shipment is not a 40-60 ratio anymore. They're sending them to me at a different ratio. Of course, you've got to go through other stuff with the problem as well, all the other steps, the defining of terms, the conclusion and context, and all that. I'm just showing you how the calculations change. Because other than the calculations, stuff is very, very similar to what we've done in the past. So now I want to do the same idea with a confidence interval problem. Let's come up with a different scenario. Let's talk about your breakfast cereal, and maybe you eat Lucky Charms, and you want to know the proportion of marshmallows to the whole cereal, because of course the marshmallows are why you're eating your Lucky Charms. So I have no idea what the true proportion of marshmallows ought to be, but I poured me a bowl of cereal, and I counted all the puffs, and I counted all the marshmallows. And how many total things did I count? 1,000. So it was a large bowl of cereal, and I found 1,000 little pieces of cereal. And how many of those pieces of cereal were marshmallows? 125. I'm really bummed out because there weren't very many marshmallows in my giant bowl. But let's come up with a 95% confidence interval for the true proportion of marshmallows that the cereal company puts into the Lucky Charms. So P hat is going to be 125 over 1,000. Z star, do you remember Z star for a 95% confidence interval? 1.96. And now I've got to do the square root. So it's the square root of, Now here's where the first wrinkle of chapter 12 comes in. I don't know P. So on this formula over here, we wrote P times 1 minus P, but I don't know P, because P is the true proportion of marshmallows they put in the cereal. And if I knew the true proportion of marshmallows that were in the cereal, I wouldn't bother finding a confidence interval for where that true proportion was. I would just tell you the answer. So I can't do the formula the way we've got it written. I've got to make a slight modification and put hats right there on top of that formula. So that's the way the formula is actually going to look with a confidence interval. So this is 125 over 1,000 times 1 minus 125 over 1,000. All of that's over 1,000. Of course, I'm too lazy to actually work that out the long way, but the good folks at TI made a function, stat test, 1 prop z int. So I go to 1 prop z int. I would encourage you to do this on your own and not just watch me do it, so that you make sure you know how to find everything and do everything. But there's the values that I stick in, the number of successes, the number of total attempts, 95%, chicka chicka whir. Based on my bowl of cereal, I'm 95% confident that the true proportion of marshmallows to the rest of the bowl is somewhere between 10.45% and 14.55%. And that's the math for a confidence interval. So none of that should be terribly different or surprising or confusing to you, but that's how you do proportions with confidence intervals or hypothesis tests. Okay, so then we need to talk about the conditions that are necessary for this. And the conditions for proportions are just like the conditions for everything else. We actually covered them back in chapter 9, but let's see how they relate again to proportions. So what's the first condition, the omnipresent condition? SRS. So I need the data to be from an SRS. In other words, for this first example, I need the eggs to be a random sample of the ones that they ship me. For the other example, I need my giant bowl of cereal to be like a random sample of the way they mix the cereal. So if it had all settled in the box or something, that could be problematic. All right, another condition. What's another thing that I need to always have? The sampling distribution has to be approximately normal. Exactly. Same thing here. How do I get an approximately normal sampling distribution? Large sample size. Now, how does a large sample size look here? In chapter 11, we said the larger the sample size, the less the data had to be normal looking. But here, I don't, it's going to take a slightly different form. N times P has to be bigger than 10, and N times 1 minus P has to be bigger than 10. You might recall that we've also said that means the number of successes is more than 10, and the number of failures is more than 10. If both of those things are met, then I can work the problem. Because if both of those things are met, then I end up with a distribution that's close enough to normal to allow me to have this work. And so those are going to take slightly different forms. For the hypothesis test that we did first, we look at this 0.4 right here. And is n times 0.4 more than 10? In this case it is, so I'm good to go. Is 0.6 times 45 more than 10? Yes. So what that says is, if I took a sample of size 45, I would expect to get at least 10 successes and 10 failures. So I'm good to go. Now with this problem, we look more at what we actually got than what we expected to get. So I would look at this 125 and say that's more than 10. 1,000 minus 125 is also more than 10. So I'm good to go. So sometimes when I look at this formula, instead of NP greater than 10, it's actually NP hat greater than 10. If it's a hypothesis test, I do NP because I think I know P. If it's confidence interval, I do P hat. And there's one more condition that I need to do. Total population size needs to be more than 10 times the sample size. So you never want to sample more than 10% of the population, or your estimates for standard deviation are a little bit off, a little bit biased. So those are the conditions we need for proportion problems. And other than that, the steps are identical to what we did before. Step 1 is the setup, state the terms, define it, tell me HO and HA. Step 2, talk about the conditions and check them. There's your conditions, apply them to the problem. Step 3, do the mathematical calculations. Step 4, conclusion and context. Same thing as what we did before. So there's one more type of problem that they go over in section 1 of chapter 12, and that's a sample size question. So let me give you the context and we'll work through this and understand how it works. Suppose that there's 2 candidates running for mayor in a certain town and you're employed by one of them. You want to take a poll to see what proportion of people in the town are going to vote for your candidate. You know you need to get a random sample. You want to conduct a 95% confidence interval, and you want the margin of error to be no more than 3%. How many people should you sample? So if I'm dealing with a margin of error problem, which formula am I going to be using? The one for hypothesis test or the ones for confidence intervals? For confidence intervals. And hopefully you recall that the margin of error is this stuff here, the stuff after the plus or minus. So the margin of error equals Z star times the square root of P hat times 1 minus P hat over N. Now I know I used an inequality here for the margin of error, but I personally prefer to work it out as an equality, because I found that young stat students, and sometimes the teacher of young stat students, messes up the inequality sign. We forget when we've got to change it to face the other way. And so I'm just not even going to have it. I'm going to use it as an equality. And I know if I find the number of people that will give me exactly this margin of error, what happens if I take a larger sample size? I get a smaller margin of error, which is fine. Smaller margins of error would be fine. So when I get my answer from solving this problem, I'll just round it up, and I know that that number or any greater sample size will do what I need to do. So let's plug the stuff in here. The margin of error we said is 0.03. What is Z star? 1.96 square root On the bottom is n, because that's what I'm looking for. Now, what is p hat? Well, this is a little bit problematic because I haven't even done the sample yet. So I have no idea what p hat is. Could I use p? No, because if I knew the true proportion that would vote for my candidate, I wouldn't waste time taking a sample. I'd just tell the answer. So you guys are going to love this. What I actually use in here is a little different. It's p star times 1 minus p star. Now, do you remember what I call p stars or what I call stars? They're magic made up values. Critical values are what the book calls it, but I call them magic made up values. So this number, this p star, is some made up number that I'm going to have to stick in the problem. Now, hopefully it's made up with some, reason, but it's just made up because I don't know what the proportion is because I haven't even taken the sample yet. For this particular problem, we're going to use 0.5 as the p star, and I'm going to show you why in just a second. But here's the stuff that I've got. I want you to pause the video, figure that out on your own. It's not hard, but lots of people have a difficult time solving that algebra. So we got 1067.1, which means if you take a sample size of 1068 or more, then you'll end up getting a margin of error of 3% or less. You can't sample 1067 because that wouldn't quite give you the right margin of error, but 1068 or anything greater would work. Now the question, of course, is why I chose 0.5 for what I did. So here's what I want to do to kind of explore that. We know that if I use p star for this particular problem, if p star was 0.5, then I ended up needing to ask 1068 people. So what I want to do is change p star to a few different values. And let's see what sample sizes we need for each of those. So I'm going to give each of you a different number to do here, and we'll work the whole thing out. Now, I won't swear that all these numbers here are correct because you guys gave them to me without a whole lot of confidence, but the point will be made even if one of these numbers is off a little bit. Notice how the sample size is getting increasingly smaller as the p star value is getting increasingly bigger. Notice also, for example, that if I had asked you to do p star of 0.4, you'd get the same thing as that. Whether it's 0.4 or 0.6, you get the same answer. So here's the question. I got to come up with a sample size that'll get my margin of error where I want it to be without knowing what the true proportion is. So I put myself in the worst case situation. And basically, what your book says is if you suspect that P is somewhere between 30 and 70, use a P star of 0.5. Notice there's not a huge amount of difference between 897 and 1068. It's 171 more people. That's not a huge difference. But as you start going down this list, we dramatically drop off. And so if your number is not in here, the main idea is to use a P star closer to 0.5 than what you think. So in other words, if you suspect that they're going to get 80% of the vote, use a P star of something like 0.75. If you suspect they're going to get 90% of the vote, use a P star of 80 or 85. But if you suspect anything in this interval, anything between 30 and 70, you might as well go ahead and use 0.5. How come? Let me show you another deal. Let's say that you thought, let's say that you only interviewed 200 people, okay? If I interviewed 200 people and the answer turned out not to be 95, but it turned out to be 90. So let's see, what would this be? What is the margin of error with a 95% confidence interval where the true proportion is 90%. And I interviewed 203 people. So zero point 0.9 times zero point 0.1 divided by 203 square rooted times 1.96. The margin of error here is 0.04127, not underneath the 30% that it, or the 3% that it needed to be. You guys see that? So if it turned, remember on this problem, here's the way I just worked it. I used the P star of 95 to figure out how many people to interview. But when I actually worked it, it wasn't 95, it was actually 90. That didn't get the job done. So you always got to make sure that you sample a slightly bigger sample size, which means your P star is slightly closer to 50-50. Anybody got that? Now, somebody else in last period said, well, Coach, why wouldn't you just always use 50-50 then? Well, here's why. You're the consulting company, and the guy has paid you to get within 3 percentage points, a margin of error of 0.03. And it turns out that the guy is going to win by a landslide. So you could have interviewed 385 people. Instead, you interviewed 1,068 people, like 3 times more than you needed to. You wasted a lot of energy. You didn't need to do all that. And it wouldn't take you very long if this was your business to figure out, I don't need to waste all that time. If they're paying me for 3%, a 3% margin of error, let's get a reasonable sample size to go through and do it. That's section 1. All that stuff is what we just did. There's sample size problems like this one. There's the conditions. There's hypothesis test, and there's confidence intervals. And that's all the stuff you need to know for section 1.